Okay, we're going to work on a problem here in region 2, as I'll call it, region 2 of the buffer solution. Sorry, there we go. So this is region 2 of the titration problem, in which you are in the buffer region. Okay, we haven't reached the end point. In this one we actually haven't even reached the halfway point, but it doesn't matter. We've just started to have a titration of a weak acid, acetic acid, and now we've added in a strong base. Remember, you can consider a strong base just adding in hydroxide ions. Okay, in this problem here, you can see we've got 100 milliliters of 0.1 molar acetic acid, and we have 20 milliliters of sodium hydroxide, 0.1 molar. So they look like they're equal concentrations. Our first step here is to recognize what's in the solution, and you can see that there's potentially sodium ions, hydroxide ions, there's the acetic acid, of course there's water. One of the questions you may have is, why isn't sodium hydroxide one of the major species? And we need to remember that strong bases dissociate 100%. And so that means if you were to try to look around this, dissociate. And so that means if you were to put sodium hydroxide in water, you'd find nothing but sodium ions and hydroxide ions. You don't find any NaOHs hooked together. They're all dissolved into that. Okay, and then the question is, why isn't there any hydronium ions from the acid? Why isn't there any of the anions? Well, that's because it is a weak acid. And the equilibrium constant for this reaction is so small that you don't get these species. Now, we often have in class been talking about the hydronium ion, which is actually what you get when you add water and the anion. If you didn't add water, you would just have it dissociating into hydrogen ion and the acetate ion. Okay, so what we have here now, and since we started to add hydroxide, we're going to have the reaction of acetic acid with just the hydroxide. Drop the sodium because it's a spectator. We need to fulfill step 1's requirements, and that's to figure out what's happening by stoichiometry. So we need to figure out the number of moles that's in there. So I have a little calculations I'd like to do for moles, and let's do that for acetic acid. Well, there was 100 milliliters, but that's 0.1 liters, and it was a 0.100 molar solution. And so you can see we have 0.0100 moles. So we're going to construct what I call, I've called them an ice table. Here's a before, change, and after, but our initial change and then a new initial. And then we're going to do something new called the molarity that we're going to figure out. Okay, we also need to figure out the number of moles of our other reactant, sodium hydroxide, because that's what you're adding into it, so it becomes a reactant. So we have, this was also 0.1 molar, but we only had 20 milliliters, or 0.020 liters. So that means we only have 0.0020 moles after our liters cancel out. Okay, and then of course that number is written there. We can assume we don't have any acetate to begin with, and so we work through the change, and the change is going to be subtracting out the least number of moles of our reaction, any of the reactants, so the limiting reactant. And the reason why we have to react all of the moles up to the limiting is because the K is so huge in the reverse direction. And why do we know it's huge? Because it is the reverse of a KB expression. If you can't see that, we do have a tutorial helping you to see the differences in those. Alright, the next step then is to subtract all the moles of the limiting reagent, which in this case is sodium hydroxide. Okay, and then you do subtraction, and you can see that there's 0.008 moles remaining of the acetic acid, but we've created 0.002 moles. At this point, though, we need to figure out the total volume that's there, because we want to figure out the pH that's in our flask that's containing the solution. And so we added in 100 milliliters, or 0.1 liters, and then now we've added in 20. So altogether it's 120 mils, converted into liters by dividing by 1,000. Then we take both of these numbers, divide it by the total volume in liters, and we can determine the concentration of our weak acid and our weak base. Notice there is no more hydroxide ion, so it should no longer confuse us in any of our calculations. So the next thing you can do is to go ahead and calculate the molarity of each one. Well, we did that, but we can set up an ICE table to figure out the hydronium ion concentration that will result from this new equilibrium that we'll have to reestablish. So we set up an ICE table with the acetic acid and the molarity we got from our previous step, and then here's our acetate ion. This is a buffer system, and so our change then is going to be X, because these are weak and we're not sure how much it's going to be, so it changes by X, and we gain X on this side and X on this side. Well, some of you, may ask, how do you know it's minus X here and plus X? I need to shift this reaction to the right to create something here. Must create something in order to establish the equilibrium. So that's why we shift to the right. We lose some from the reactants and gain on the products in the way we've written. So we have our new equilibrium, and now we can set up the equilibrium expression. Notice that this is set up in the Ka, and this was given, so we can go ahead and write that and set up our formula here, the products, which is X times 0.0167 minus X, all over the reactant concentrations. Minus X, actually this one's plus X. But since the equilibrium constant is so small relative to these numbers here, we can assume the approximation, the 5% rule, or the 100K rule, and that tells us then we can drop those X terms there and multiply now both sides by 0.067 and divide by 0.1067, and we can find that X, which is the hydronium ion concentration, is equal to 7.19 times 10 to the minus 5. Okay, now let's find the pH, which is the minus log of this number, and we can see that that number is 4.14. What you could have done instead of doing that is the Henderson-Hasselbalch, and to recognize that you do have some concentration of a base, the conjugate base, and the conjugate acid. So we could have just done a Henderson-Hasselbalch. You do not need to do both of them. Just pick one. I think this is a little bit faster. So we put the concentration of the weak base on top. There it is. Actually, you don't consider it equilibrium. You can just put the initial numbers in there. Okay, we would assume, this is, remember, an ICE table, all in one chemical, or in one formula. The pKa is 4.74, the minus log of 1.85 times 1.8 times 10 to the minus 5. Well, this becomes plus the log of this ratio. Well, this ratio, when you do the math in your calculator, is 0.250. And that turns out to be minus 0.601, but when you do the subtraction, it's 4.14. That is the same as what we got before. Okay, there's our Ka and there's our pH, and so it doesn't matter which way you do it, you get 4.14 as the pH at this point here in the buffer region of our titration problem.